Hey everyone, and welcome to my tutorial on Matlab's Numerical Ordinary Differential Equation Solver. Now, this will hopefully be the first of 3 videos. In this first video, I kind of just want to introduce this ODE solver, or really set of ODE solvers. What they're looking for, their inputs, how to program them in MATLAB, so on and so forth. And since I'm just introducing this, I'll only be dealing with examples in one dimension, although I will have examples with constant and non-constant coefficients. In a second video, hopefully I'll be talking about two-dimensional examples, and these can correlate to higher dimensionality or, higher degree of freedom systems. And in the last video, I want to talk about an events function, or what most people will call an events function, which you can use in MATLAB to stop the ODE solver early, depending on certain conditions, blah blah blah. But now we're here. Now, if you're already familiar with MATLAB's ODE function, what it does and what the inputs are and how to get them and set up the problem, and you're just thinking, okay, well, I don't need this, just show me the examples, there should be some annotations over to the side. If they're not there for any reason, there should definitely be links in the description below so that you can skip ahead to whatever parts you want to skip to, and hopefully that'll be useful. As a heads up, I'll be talking about Matlab's ode45 solver. If you're used to using one of Matlab's other numerical ODE solvers, like say, ode23 or ode15i or whatever, don't be worried. The same process that I'm about to describe will work for all of those guys. You can check Matlab's documentation, to see that it has various numerical ODE solvers, depending on the accuracy you're looking for, how crazy your function is, and how much time you're willing to spend for a solution, so on and so forth. And it'll give you a list of these guys, right? So just check there and you'll see what other functions work with what I'm going to describe. I'm used to using ode45 as a Mechie student at the University of Maryland College Park, but to each his own. So MATLAB's ODE solver, specifically ode45 solver for me, what are its inputs? What is it looking for? Well, it's going to have 3 inputs, generally. You can have more for special options, but we'll get to those later. It's going to have 3 inputs, all of which are going to be vectors. The first of these inputs is going to be the derivative of your state vector. Now, if you aren't familiar with state vectors and, state space, blah, 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 don't worry about it. We'll get to that soon. But it's going to look for the derivative of your vector of states as some general function of time and the components of your vector of states, which will just be state variables. Again, we'll talk about that soon. Now, you might see other notation besides this. Some people prefer to say, some y prime equals some g of ty. MATLAB's documentation actually has this notation. Maybe some people prefer to use g of tx. It doesn't matter. A variable is a variable. I like to use s so I don't get mixed up if I'm solving for, some x or y function. But again, to each his own, right? So that's the first input. The second input is going to be the time span, which is really easy. It's just going to be a vector that has the initial condition, the initial time that MATLAB will integrate from, and the final time that MATLAB's numerical integrator will stop at. Now, there's another way to do this. Let's say you want to, when you get your solution, you want to have values every 0.5 seconds. So I want to know the values of everything at every 0.5 seconds. Then I can just do this. Again, have my initial time here, put a colon, the size of my time step, in my case 0.5, and then the final time at the end, with this colon guide right here. Now, this will not affect the time step that MATLAB's ODE solver will use. Each of the different numerical ODE solvers use different kind of time steps so they can adjust the accuracy and such. This will not impact the time step that it uses. All that it will do is just allow you to get the solution at values that you want, as opposed to just being values at the time steps that MATLAB automatically uses. So don't worry, this will not hinder the accuracy of your solution. But that's the time span. So the third input is going to be the initial conditions. So maybe you have some X naught, some Y naught, which is a Pokemon, if any of you get that reference. Maybe you have an initial velocity, blah, blah, blah. And boom, there are your initial conditions. Now these initial conditions will correspond to the initial time you give MATLAB. So if these guys are the time at, say, some t equals 2 seconds, then this initial time should be 2 seconds. That should stand to reason, but yeah, putting that out there just in case. So these two guys are pretty easy and straightforward. What most people have questions on is this derivative of your state vector. And this is honestly easy to get. Most of the trouble comes from getting the vector of states itself. The derivative is pretty easy. So let's talk about that for a little bit. This vector of states S. Now if you haven't heard or learned about state space and all that stuff, I'm not going to leap into a lecture about it. I want to keep this simple in a way that most can understand it. So professors and smart people who learned more about it, please don't come after me. But in simple terms, you can think of your vector of states as just being a vector with variables S1 to Sn. These are your state variables, S1 to Sn. And n is the order of the differential equation that you're working with. But you can think of your vector of states as being a vector with state variables S1 to Sn, where these variables represent the function that you're solving for and its derivatives, all the way up to the n-1th derivative. So let's say I'm solving for some x of t. Then S1 is x, S2 is x dot, S3 is x double dot, so on and so forth, all the way down to the n-1th derivative, which will be Sn. So it's a pretty simple definition. Although people get confused by it sometimes, it's really not complicated, so don't freak out with this notation. Let's do a quick example, for instance, to show how we set this up. So let's say we have this really easy ordinary differential equation here. This is super easy, alright? This is a third order differential equation. Now since the order is 3, what that tells us is that the vector of states will also have a length of 3. So we'll have S1, S2, and S3. And following the notation we had earlier, the description we gave earlier, that tells us that S1 is x, S2 is x dot, and S3 is x double dot. And from there, getting the derivative of your state vector is really easy, right? Doing a time derivative is very easy. So the derivative of your state vector, S dot, will just be S1 dot, S2 dot, S3 dot in this case. And again, looking at our notation here, if S1 is x, then S1 dot is going to be x dot. If S2 is x dot, then S2 dot is going to be x double dot, and so on and so forth. So likewise, S3 will be x triple dot. So now we have the derivative of the state vector, like MATLAB wants, but you have to recall that MATLAB wants the derivative of your state vector in a very particular way. If you recall what we said earlier, MATLAB wants the derivative of your state vector as some general function of time and your state variables. So can we do that here? Well, if you look closely, x dot is just s2, x double dot is just s3, so we can put that in. Put that in right now. We have s2, we have s3, but x triple dot is not one of our, is not defined by a state variable here. So we don't have x triple dot as a state variable. However, if you pay attention to what this definition implies, right, about the state vector. The state vector has state variables that represent the function we're solving for and all of its derivatives all the way down to the n-1th derivative. What this means is if we can get the highest order derivative or the nth derivative in terms of all the lower order derivatives, then we can get the highest order derivative in terms of state variables. And we can do that very easily here. If we just shift these terms over to the right side of the equation, that's going to be done. So if I move these guys over, I'm going to have negative x double dot minus x dot minus x. And again, recalling from over here, x double dot is just s3, x dot is just s2, and x is just s1. So we can substitute that guy in now, right? Let's substitute in that expression. And for x triple dot, we get s3 minus negative s3 minus s2 minus s1. Here we get s3, here we get s2, and now we have the derivative of our vector of states in terms of time and the state variables. So we're done. Now, don't let it freak you out that the variable time doesn't necessarily appear in this vector. That's okay. Recall that we're really ultimately solving for a function of time, right? So we're fine. What you want to make sure is that this vector, when you're done, will only have the variable time itself, some function of the variable time, and or the state variables. If it has anything else besides those, for instance, in this case, x triple dot, which is not a state variable, then you still got some more work to do. But that's really all there is to, getting the derivative of your state vector. It's not really that complicated, if you can see. So let's go ahead and do an example and pop that guy into Matlab. Now, a lot of you guys are probably used to the stereotypical second order differential equation that's linear with constant coefficients. So let's do something that's more fun but not too crazy. Let's say we have some t squared times x double dot plus the sine of t times x dot plus x times e to the t, the exponential of t, equals 5. This is more fun, but it's really not that complicated. As you can see, again, this equation is second order this time, right? The highest order is 2, so our state vector, our vector of states, is just going to have size 2. So we have S1 and S2, and those guys are just going to be x and x dot. Likewise, s dot is just going to be x dot and x double dot. Alright, now as we can see, as with before, we're going to have to re-express the highest order derivative in terms of the lower order terms. Again, that's really easy. Just isolate this guy here. We can do that by moving these guys over to the right and dividing by t squared. So let's do that. If we do that, we end up with x double dot equals 5 minus the sine of t times x minus x times the exponential of t, and this whole thing is going to be divided by t squared. So there, that's pretty easy. Oh, I made a mistake here, sorry. This should be x dot, not x. Now remember from this vector over here, right? X dot is just S2, and x is just S1. And same for this guy over here, this guy is just S1. So now if we want to write out S dot, we will get this guy. So for the bottom, we have this huge dude, 5 minus the sine of t times S2 minus S1 times the exponential of t, and all that divided by t squared. And then up top we have S2. Oh my goodness, I wrote this wrong up here too. I'm sorry guys. X dot is S2 per the notation and such. So we have the derivative of the state vector in terms of the state variables and time, right? And this time we do actually see time appearing in this vector. Now all we need to put some meaning into this and make this usable for MATLAB is give ourselves some initial conditions. So let's say the initial conditions are x of 1 equals 1 and x dot of 1 equals 0. So we have our initial conditions here, and since these initial conditions correspond to 1 second, our initial time is obviously going to be 1 second. And let's just say we're interested in finding out what happens 30 seconds in to this function, right? So that would give us our t initial and t final here. So now we have all that we need, really, to go ahead and jump to MATLAB. So let's get into some programming. Alright, we are now in the MATLAB programming environment. Quick comment, I realized that I said t squared just a few moments ago, but I wrote that 2 a little bit lower than it should have been. I'm sorry, I meant t squared, writing mistake. There are a couple writing mistakes back in that video, but it's okay. So, anyway, we're here in MATLAB's programming environment. I've already set up 3 empty M files for 3 different kind of ways that you can go about using MATLAB's ode45 solver. I'm going to call them 3 methods. I'm going to call them the M file method, the function method for the second one, and the function handle method for the third one. These aren't so much distinct methods as they are sort of minor different ways that you can go about programming this stuff when you're trying to use MATLAB's ode45 solver or other similar solver, right? But they do affect the options that you'll have when you are doing your programming, so they're important to be aware of. I'm going to start out with the mfile method because it seems to be the one that most teachers and YouTubers will talk about, so I'm assuming it's most familiar. So let's start out with that. Now quickly, I want to remind you guys, and I'll put this in a comment, MATLAB is going to look for s dot, right, the derivative of our state vector. And it's looking for this guy as some general function of time and our state variables, which are components of our state vector. Now that being the case, notice that this is a function. Since MATLAB is looking for a function that gives us s dot, we're literally going to make a function. I'm pointing that out so that this programming process makes sense. So we're going to create a function that returns s dot, and it's going to be a general function of time and the state variables. Now, since the name of this M file is ODE Nightmare 1, I'm forced, due to programming reasons, to call this guy ODE Nightmare 1, right? That's just how the rules go. But generally speaking, it doesn't matter what you call your function. You can call it whatever you want to, really. So I have this function that I'm intending to return s dot. Another comment I want to make to remind you guys is that s, right, our vector s, is our state vector, as we mentioned earlier. And since it is a vector, it's going to have indices. It's going to have components. In our case, in the example that we did, this vector is going to have two indices, right? So it's going to have index 1 and index 2. And that's the notation that we use in MATLAB to refer to indices. Hopefully you know that by now already. But it's going to have these two indices, which are representative of the state variables s1 and s2 respectively. These, oh my goodness. Now these state variables in turn represent x and x dot. So x is represented by state variable 1, which is index 1 of our state vector, and x dot is representative of, or is represented by state variable 2, which is the second index of our state vector. Okay? Now when we program in MATLAB and when we're referring to the state vectors, we're going to use this notation. We're going to use the index notation. And MATLAB is already assuming that when you refer to the first index of your state vector, you're referring to the first state variable, right? State variable 1. When you refer to index 2, you refer to state variable 2, so on and so forth. That's what MATLAB sees, and that's how we're going to write it when we program it out. So let's declare s dot, and let's declare it just the way we wrote it. For the first component of s dot, we have state variable 2, so I'll reference the second index. And for the second part of s dot, it's some long complicated nonsense. 5 minus s2 times the sine of t minus s1 times the exponential of t, all that divided by t squared. Yippee-ki-yay. Is there a mistake? Yes, there is. This parenthesis does not belong here. Okay. And this function, that's it. We have a function that is going to give us s dot. It's a general function of time and our state variables, and we've expressed it right here very clearly. Now when we're using the mfile method, we have to call ODE45 outside of the actual mfile itself. But since it's its own mfile and its own function, we can call it in the command window, we can call it in a new mfile, we can call it anywhere else, as long as we're in the same working directory, the same current folder as the mfile itself. So that's pretty cool. So I'm going to call it in the command window. I'll explain these two output variables in a moment, but I'm going to call ODE45. Let's see. So for the inputs, like we said earlier, it's going to ask for the function that gives us s dot. In this case, that would be ODE Nightmare 1. It's going to ask for the time span, which was 1 second to 30 seconds. And it's going to ask for the initial conditions. And we had x naught being 1, we had x dot naught being 0, and that's that. Now when you're doing this, you might have seen some people or some professors surround the name of the function in single tick marks or apostrophes. And that is a way to get this done, but I strongly advise that you do not do that. Please do not do that. Instead, put an @ symbol in front of the name of the function. Doing both ways allows you to get a solution from MATLAB, but if you put the single tick marks around this function, then it will take longer, for one thing. There are two problems with using the apostrophes. The first problem is that it'll take longer. So I ran this through with the apostrophes, I ran this through with the @ symbol. When you use the apostrophes, it takes more than twice as much time approximately to get a solution from MATLAB. That's crazy. So first of all, we want to avoid using the tick marks to speed up the process. Secondly, and this is kind of a weird thing that happens, sometimes depending on what you're doing, you can run into weird errors with MATLAB. I've seen some friends who were trying to do some advanced options in MATLAB, trying to stop the ODE solver early, again like we'll be talking about later, and they're using these quotation marks or apostrophes, and MATLAB was returning errors saying that there are symbolic variables or other things going on, when clearly they weren't trying to assign any symbolic variables anywhere, they were just referring to their function. But MATLAB didn't see it. So there are probably certain mistakes that are made to cause that in someone's programming, but it's best to just avoid that altogether and use the @ signs. No, that was a huge rant, but it's important that you guys know that. This way is faster and safer. Now let's talk about these two output variables. As you could guess, this first output variable is going to have the times, right? It's going to have the time values that our state variables are evaluated at, from our initial time to our final time, which in our case is from 1 second to 30 seconds. That'll be what this guy is. Pretty straightforward. Likewise, as you could imagine, this guy called state values is going to have the solutions for our state variables. So that's cool. Specifically speaking, this is going to be a matrix. It's going to be a matrix whose columns hold the solutions for the state variables. So the first column will hold the solutions for state variable 1 that correspond to the times given. The second column will hold the solutions for state variable 2 for the times given, so on and so forth. Now in our case, we only have 2 state variables, so we're only going to have 2 columns in this matrix, but that's okay. So I'm going to call this function, hit enter. This time span is a bit big for this interesting differential equation that we're dealing with. So I'm going to skip ahead a few seconds so that we can see the results. We're here, we have the solutions, they're in our workspace. I'm going to extract the 2 state variables. So I'm going to extract x. Remember, x is referenced by state variable 1. So I'm going to extract the first column into what I'm going to call x. Likewise, x dot is referenced by state variable 2, is represented by state variable 2. So I'm going to extract the second column of state values into this variable that I'm calling x dot. Alright, and now I can plot what I want. I can plot x against time, or x dot against time, or something else. I'm going to plot x against time in a figure. So let's do that. See what we get. Here's our nice solution. I guess a little more interesting over towards this end. But this is the solution to this differential equation. You could run this differential equation through something else, like say Wolfram or something. You'll get the same solution. So we know this is okay, this is right, this is fine. You might see a different time window depending on the options you give, but this works. So this is good. I'm gonna title this because I'm gonna show that all the plots are going to be the same, that all of our methods are going to work. And alright, awesome. So that is the mfile method, and that's all there is to that. If you aren't interested in seeing the other methods, you can just skip ahead to the other examples. Or if you're done here, you can just leave, you know, whatever you want to do. But for those who are sticking around for the ride, let's go ahead and move on to the function method. This method won't really be too different from the function, from the mfile method. And you'll see what I mean in a bit. So I'm going to call this guy, and this time I'm going to declare the values. So the initial time is 1 second, the final time is 30 seconds, the x naught is 1, the x dot naught is 0. Okay, I'm going to declare the time span, t naught tf. I'm going to declare the initial conditions, and that is going to be IC equals x naught, and x dot naught. Cool. And now we need to call ode45. But before that, we need to create the last input, which is, again, a general function of t and the state variables that gives us s dot. Now when you're using the function method like this, you're going to create your own separate function at the end of this m file, right? But I'm going to actually copy all of this because the code is pretty much going to be the same. I'm going to copy all this and paste it over here. The only thing I'm going to change is this name because I can change it now. I'm not restricted by this the whole naming issue that I was earlier. So I'm just going to call it G. And now I have all the inputs. So I'm going to call ode45 here. So let's go ahead and do that. Our function in this case is called G. Again, you can use the apostrophes or you can use the @ symbol. Again, it is much better to use the @ symbol. So the @ symbol, we have the time span, we have the initial conditions, and those guys are going to go here. So as you can see, there isn't really a difference in the coding between these two methods. I pretty much copied this code and pasted it at the end of here. The difference in using the function method is that this m file is the only file that has access to this function, right? So I can't call this general function G in the command window or in some general other m file because it's declared separately at the end of this m file, so only this m file can see it. In turn, this method is just slightly faster in some circumstances, so there are still some advantages to using it. I'm going to go ahead and extract the values for x and x dot when I call this function, because why not? X dot equals state values this, and I'm going to also plot time versus x in a new figure. So I'll make figure 2, I'll clear the figure, I'll have it plotted, and I will title it figure 2. I'm just doing this so I don't have to write it in the command window. And I will change this so that I receive x and x dot directly as individual variables. Okay, so this guy is all done. I'm going to call it down here. I'll clear the variables and the command window, and I'm going to declare this function. So, or call this function that I just wrote. So time x dot equals ode nightmare 2. Again, I'll skip ahead to after the solution is gotten. Okay, cool. Here's our solution. Here's our plot. It's the same as the first plot, so we know that both of these answers agree. Both of these answers are correct from the mFile method and the function method. And because I took care of these lines of code here inside this mFile instead of the command window, I was automatically able to get x and x dot when I called this guy, and I was automatically able to have the guy plotted too. So that's nice, just having things done cleanly. So that's the function method. Clearly not much difference from the mFile method. You're just declaring it at the end of an mFile as its own separate function. But it is just slightly faster sometimes. That's the main difference. Now finally, we're going to be dealing with the function handle method, which, as you could probably guess, is going to deal with function handles. Again, not much is going to be different. I'm going to copy and paste all of these declarations for the constants, and I'm going to copy this comment code because it's good to have your code commented. And now, instead of writing an actual function, I'm going to make a function handle. So I'm going to have this @ symbol. I'm going to make a function handle that's a function of t and s. And again, this guy is just going to return to me s dot. So I'm going to write it the same way that we've been writing it here and here, the same way we wrote it by hand earlier. And there. Well, let me get rid of this weird part here. Whoops. Okay, and there. So now we have a function handle, which is still a function that's giving us s dot. We're just calling it with a function handle instead of an actual function. I called it s dot this time to remind me that it's returning to me s dot. But that's all. So now we can just go ahead and do what we did last time. And to do that, I'm just going to copy these lines of code again, because everything outside of that is pretty much the same. Right, we're going to call time and state values. We're going to have these guys be the outputs. We're going to extract x and x dot. I'm going to plot this in a new figure, and I'm going to title it figure 3. And now the name of this function is not g, it's s dot. Now you don't need apostrophes or an at symbol this time because it's a function handle with a nice happy at right here. So I'm just going to leave the name of this function alone. And again, I'm going to call this guy. Well, let me first clear, and then let me call ODE Nightmare 3. I'll skip ahead to the solution. Okay, and here is the solution, which is the same as this guy, which is the same as this guy, right? So all of the methods agree. The mfile method, the function handle method, they all work. So that's all nice and neat. Those are the 3 methods. As you can see, there really isn't much difference. I did a lot of copy and pasting, and I hope that wasn't confusing. But I did that because, you know, there wasn't much difference between them. It's just a matter of how you have to change the way you program the other stuff. For the most part, declaring s dot as some general function remains the same, whether you're using a physical function or just a function handle. There are some slight kind of pros and cons to this that I'll discuss towards the end of the video if you want to see that. Again, there are going to be skip links in the description. But before I do any of that, let's go ahead and do one more example and then run that through Matlab, and then after that we can talk about pros and cons. Okay, back to the drawing board, literally. So we're going to do one more example really quickly, and we'll be done. And this should go faster. I'm going to make this a more physical example because I like things that are more physical. And that's what we're going to do. So let's say that there's a person who is falling off of a building, and he wants to do it for the views. There's a trampoline at the bottom, but he's not telling anybody. He just wants to make a video that's clickbait, and he's having himself filmed falling off, you know, some building or whatever. Actually, I don't want these lines here. I'm going to get rid of those. So he's falling off this building, and we're interested in finding out his position, his velocity, and his acceleration from the start of his fall to 10 seconds into his fall. So what that tells us is that the initial time is 0 seconds, and the final time is 10 seconds. Keep in mind that units are extremely important here since we're dealing with physical quantities. Likewise, since we're dealing with an initial time when he just started falling off, we're just going to say that his initial position is 0 and his initial velocity is 0 as well. But this is 0 meters, so this is 0 meters per second. Okay, so we already have our time span and our initial conditions right here. All we need is the derivative of our vector of states, and to get that we need a differential equation. So looking at this person over here, We know from physics that there are two forces that should be acting on him. There is the force of gravity, which is just his mass times the gravitational acceleration. And then there is the drag force. And for the sake of ease, I'm just going to approximate this guy as a constant of proportionality times his velocity. In some situations, that is acceptable, and I'm just assuming that to be the case here. Okay, so this guy is falling. These are the forces that are acting on him. I'm going to define the x direction in this direction. Alright, and we know from physics, Newton's force equation is going to be the sum of the forces equals ma. And we know this to be the case since this person's mass is going to be constant. Now, we can very easily get a differential equation from here. Keep in mind that the velocity is just the time derivative of the displacement. So we can actually write this as cx dot. And likewise, the acceleration is the second derivative of x with respect to time. So I can write mx double dot. And if I write the forces over here on the left side and write out the whole equation, I will get mg minus cx dot equals mx double dot. And I'm going to go ahead and isolate the highest order derivative here. We see we have a second order differential equation. I'm going to isolate the highest order derivative because we'll have to do that in the end anyway. So x double dot is going to be equal to g minus cx dot over m. So this is another important guy. And now let's go ahead and deal with our state vector. This is a second order differential equation, so our state vector is going to have two components, S1 and S2. And those guys are going to be x and x dot respectively. Likewise, the derivative of our vector of states is going to be x dot and x double dot. And if we put in our expression that we just got, that gives us g minus c x dot over m on the bottom and x dot on the top. Finally, if we put in the state variables, that gives us s dot equals g minus c times s2 divided by m and s2 up top. And that is, that is s dot. Sorry if this this writing seems a little bit cluttered. But this is s dot in terms of the state variables and time. You'll notice that s1 doesn't appear in here this time, so not all the state variables are in s dot. That's okay as long as all of this in here agrees with our equations and is valid. And in this case, that happens to be true. So with this information, we can hop straight into MATLAB. Okay, we're back in the MATLAB environment. Now, I already discussed the sort of different ways to do those three different methods that I mentioned earlier, so I don't want to go through all the details again and bore you guys. So I'm just going to show you guys the already written code. Here's the mfile method. Here is the function method. And here is the function handle method. You can go back and pause and copy the code as you need to. I'm just trying to get through this pretty quickly. You'll notice that I've declared these constants, g the gravitational acceleration, m the mass, and c the constant of proportionality. These guys need to be declared. We're not dealing with symbolic variables, right? We're dealing with MATLAB's numerical integrator, numerical solver, and so I had to declare these guys. So I declared the gravitational acceleration to be 9.81 meters per second squared, the mass to be 82 kilograms, and the constant of proportionality to be 1.2 kilograms per second. So that's what I want to point out. There's all the coding stuff. I want to show you guys the plots that we wanted. Here's the position versus time. Here's the velocity versus time. And here's the acceleration versus time. Now you'll notice that the acceleration wasn't a state variable that we had, so it wasn't something that MATLAB explicitly solved for. But do recall that the acceleration was the highest order derivative in our differential equation, and we expressed that as a function of the lower order derivatives. Because of that, after MATLAB gave us the solutions for x and v, i.e. the displacement and the velocity, we could use the equation that we had for it, which is this guy, to get the acceleration. So all I had to do was say a equals g minus c times v divided by m. And I was able to get the acceleration. You will have to have these guys declared, of course, when you call them. But that's how you go about getting the acceleration. Extremely simple. Okay, so that's it. I just want to talk about some pros and cons. They aren't huge deals, but you should be aware of them when you're thinking about whichever method you want to use. The first thing to know is the speed issue. The mfile method is generally slower than the function method, which is generally slower than the function handle method. Now, these speed differences won't be so clear when you're dealing with very simple differential equations. As you're dealing with more complicated systems, the differences between the methods time-wise will become more clear. The function method is noticeably faster than the mfile method, but the function method is not that much slower than the function handle method. So that's just some stuff to be aware of. One major pro to be aware of regarding the mfile method is that, as we said earlier, it can be called anywhere else as long as you're in the same folder as the file itself. So I can call this in the command window, I can call this in another mfile, be it whatever, some mfile called Swiss cheese, called turkey, called whatever else. I can call it wherever as long as I'm in this folder, the same folder as the function itself. That's awesome, and that's something that these other two methods are not able to do, due to the fact that the function, whether it's an actual function or a function handle, belongs specifically to its own m file that it's in, and consequently it is not available to the command window or a separate m file. That's okay. Whether or not that's a con to you kind of depends. If you're just solving one homework problem and getting a couple of plots out, then you only really need to use your s.dot function once, and so you can just write it all in the same code, right? But if you're going to be using the function that gives you s.dot multiple times, then it might be a good idea to, to use the mfile method. Because with the mfile method, you won't have to write the same code over and over and over and over again. So that's nice. It's a major plus for the mfile. That's all the comments that I have. So I hope you guys enjoyed the video. I do apologize. I know that it was long, but I just wanted to make sure that I was going into decent detail on things so that you can understand what's going on and make sense of it, see it intuitively, as opposed to sort of just trying to regurgitate information that you're given. So hopefully that helped you towards that end. Let me know in the comments below how it went, what was helpful, what wasn't, any ways that I can improve this. And yeah, so that's it. Good luck on your MATLAB ventures.